Bismillahirrahmanirrahim. Let's take up joint stiffness next. And in joint stiffness, we'll start with bolt stiffness. And later on, we take up the member stiffness. Now, the bolt, as a result of tightening of the nut or screwing in of the bolt, undergoes tension. The member will go into compression, but the bolt undergoes tension and there will be some deformation and a force will be there as a result of tightening of the bolt, and therefore the stiffness comes into play. So if this is your bolt and this is your nut, then the total length of the bolt will be L, and the length of the threaded part is LT. Also, the gauge length, anything that goes between the head of the bolt and the nut, that is the gauge length. And the gauge length in turn is a combination of the length of the threaded part LT and the length of the shank part or unthreaded part LD, and this is the major diameter of the bolt. So this is your bolt, and because it is composed of two regions, there's a force will be applied on this, but this comprises actually two parts, threaded part and the unthreaded part. So first of all, let's consider a cylindrical bar subjected to a load P. The cross-sectional area is A and the length of the bar is L. As a result, this undergoes a deflection delta. Now, because stresses and strains are connected with this stiffness of the material, Young's modulus, we can write the formulas for sigma and epsilon. This is a 1D system, so the stress is P over A, strain is change in length over original length, or PL over A delta. Now this thing, P over delta, this is actually K. K is equal to P over delta. Now this means that K is AE over L. Just take these to the other side, and this is your expression for a bar, the stiffness of a bar subjected to a load P. Now, because our problem is a combination of two bars in series, this is unthreaded part, this is the threaded part, because whatever is happening inside. So you have this sort of a situation. Now there will be a KD here, there will be a KT here, unthreaded part, threaded part. There will be an area D, area T. There will be LT, thread part length, LD. Two parts in series. So what if this is subjected to a load P? There will be some deformation, but this time the deformation will be a combination of deformation in this part plus deformation in this part, or in other words, you know what K is. K is P over delta, so delta is equal to P over K. So P is the same, it's the same force passing throughout. P over KD plus P over kt or p1 over kd plus 1 over kt. Now this over this becomes, and what is this but the reciprocal of the stiffness of this whole arrangement, that is the bolt. Therefore you can write it like this: 1 over kb is equal to 1 over kd plus 1 over kt. Here b stands for bolt, stiffness of the bolt. It's whole combination of unthreaded and threaded. Now uh, if this is the case, then you can simplify it further. kd kt kt plus kd, 1 over kb is this, or in other words kb becomes kd kt over kt plus kd. This is your stiffness of the bolt, which has a combination of threaded and an unthreaded part. Now to calculate this we need kd and kt. Now using this expression, because this is a combination of unthreaded and threaded, so you have to use this expression, and using this expression kd will be ad. ee is the same because it's the same material, so no need to write d or t here, ld. Whereas for kt you adapt this in this form. Now this AD, very simply you can calculate pi by 4 d square. D is the major diameter. As far as this LD is concerned, LD is simply LD, L total length, that will be dictated by the thickness of the plates and whether there is a washer or whatever, then the size of the nut, and then whatever you get in the preferred table. So this one it will be dictated by that. This minus LT. LT, you know, for each size of the bolt, there are specifications for the threaded part. So L minus LT will give you LT. So it's very easy to calculate this one. When it comes to this KT, AT is simply tensile stress area, and you read it off table 8.1. We have seen that earlier. As far as this LT is concerned, let's see what LT equals. LT is this part, threaded part inside the grip length. This is a small L, different from the large L. This should be L minus LD. L is the grip length, you already know the grip length depending on the situation, minus LD. LD you just calculated here. So with these values and AT and A, you are in a position to calculate this KB. KB, let's start with KD KT over KT plus KB. Put the values. ADE over LD, ATE over LT over ADE over LD plus ATE over LT, or AD AT E square over LT ADE plus LD ATE. And this LD LT, they cancel each other out. And even this can be simplified further, because you can take this e common, and then this one of the square vanishes. So you have ADE over ADLT plus ATLT. This is the expression for stiffness of the board, and you have all these values. You can easily figure out all these values for given problem. Now, once this board stiffness has been taken care of, let's come to the stiffness of the members. Now, if this was the bolt, let me draw it again. This is the bolt, this is the nut, this is the plate. These are the two plates that are actually being joined together here. Now, let's call this plate 1. This is plate 2, and there will be some, again, some threaded part and some portion that comes out of the bolt. This, you're very familiar with this one. Now, because you have two plates here, it could be 3 plates, but let's take the example of 2 plates. Normally going to be 2 plates. They are in series again, so your expression will be the same as last one. That is, for two springs in series, these are essentially two springs in series, your combination, the stiffness of the combination is 1 over k is equal to 1 over k1 plus 1 over k2, whatever the number of elements that are added together. So your expression would be the same, only this time we'll call it 1 over km for km for members, 1 over k1 plate 1, 1 over k2. And if there are more plates, then you can go on, but we are just talking about 2 plates. Let's call it for 2 plates. Actually, it's more than that, right? Now, this would have been equally simple as we just saw the case with the bolt, but actually this is slightly more complicated. The good thing about the bolt was, when you tightened this, the bolt went into tension, these come in under compression, these 2 plates. But the good thing about the bolt was, the whole area, threaded area here, unthreaded area here, it comes under tension. Here, what comes under compression is not, for example, this sort of a cylinder. If that was the case, we would simply have put in the values of this A of plate 1 and then A of plate 2, which would have been the same. But what happens is not this. Experiments prove that you have this sort of a situation. The area that comes under compression is this sort of an area. Obviously, these are connected together, so the compression effect is not directly under the head of the bolt and the head of the over the head of the nut, but they slightly diverge as you move away. Now this sort of a situation takes place, and if this is the total grip length L, then these two meet at a distance L over 2 and L over 2. This is what experiment tells us. So what goes into compression is this area and this area. So because these areas are actually not constant but variable, so for the calculation of this K1, you cannot simply use AE over L. We did this, in the case of bolt because A was constant. There were two A's, one for threaded part, one for unthreaded part, but still both of them were constant. Here, because it varies, the area varies, so you'll need to have some sort of an integration, but essentially you'll be doing the same thing. Now, this figure shows this compressed area in a 2D way, so it looks like this, but actually in a 3D situation, actually this is a 3D situation, the part of the material that goes under compression is, to draw it in 3D, it is something like this. Obviously there's a hole inside, so that you have to exclude that. I've just drawn this plate 1. Plate 2, for plate 2 you'll have plate 3, will actually combination of two, but it will be something like this. Something like this. So you have to actually cater for all these if you are going to uh, evaluate this, the stiffness of this joint. Now let's take plate 1 first. This is plate 1, this is plate 2, one part, plate 2, second part. So actually if you do this kind of a situation, if you have this kind of a situation and you have different materials, material 1 and you have material 2, then actually you'll have to consider these three figures, and these are actually frustra of cone or truncated cones. Now let's take this one first, and whatever we'll get from here we'll be able to apply on all three, as I'll show later on. And now that we have seen what it looks like in 3D, I'll again revert to 2D because it's simpler, but in your mind you should have this, that you're talking about a 3D figure. Now I'm drawing the first frustrum here, and this is D. Let's say the thickness in this case is T, and the angle of this cone, actually it's a truncated cone, but angle of the complete cone, half of the angle is alpha, and this distance, let's call this capital D. Now because this area keeps on changing, what we'll do here is we'll take a small differential slice here, and that will be at a distance x, and the thickness will be of this slice is dx. It's very familiar process for you. It's a differential thickness dx at a distance x. Now contract, this will be under compression, so it will be contracted. Contraction of dx will be this, a differential contraction, and we are going to use the same formula. Actually, this formula PL over AE, this is the same formula that we have seen before, but in this case this is a differential contraction and this length is also differential. So actually this converts to P dx over A, which is a function of x. Now A keeps on changing, it's a function of x. Here it was constant, and then E. Put in the values. Let's see what A is. A will be pi. Actually it's pi r square, but in this case obviously you have to remove this. This has to be removed. This is not there. Area is basically pi r outer minus pi r inner. So r outer is again a variable, d over 2 plus x tan alpha. X tan alpha, actually tan alpha is nothing because this is also alpha. So this is x. X tan alpha is nothing but this length, d over 2. You had reached this point plus this square, but you have to remove this part. This is simply d over 2. This is your area. It's a variable, it depends on x. Now simplifying, now this we have to put here. So this becomes p over pi e. This comes from here, and then you have dx over x tan alpha plus d over 2 x tan alpha plus d minus d. This is your expression for d delta. Now we are interested not in d delta but in delta, so that's simply a matter of integrating this d delta, which was just for a thickness dx, from 0 to t, and this p of these are constants, they come out, and the rest is the same. X tan alpha plus d over 2 x tan alpha plus d minus d over 2. Now if it can be shown that this integrates to something like this, pi e d tan alpha log of 2t tan alpha plus d minus d plus d over 2t tan alpha plus d plus d minus d. This is delta, and recall that k is simply p over delta. So just divide p by this thing, so p vanishes and some rearrangement takes place here. So your k turns out to be phi e d tan alpha over log 2t tan alpha plus d minus d plus d over 2t tan alpha plus d minus d. This is your first expression for k. Let's call this k. What we are talking about here is for this, for one frustrum, we have this expression for the k. Now there are more than one, and we'll see what happens. But this is the main expression. Now experiments have told us that this alpha, which we took as a variable here actually, for this alpha, experiments confirm that 30 degree is a very reasonable estimate from experiments. Now, obviously, it won't be exactly 30 degrees, but 30 degrees is not very far off. So if we use 30 degree here, and FEM studies have also confirmed this. So if you use alpha is equal to 30 degrees, you can simplify it further by reducing one variable. And this k turns out to be then for 30 degrees. Now this is a special case, but it is very close to the true situation. This is your general purpose equation. General purpose in the sense you have introduced this limitation of 30 degrees, which is close to the truth. So general in the sense that it will give you the stiffness for any frustrum. It will give you the stiffness for this frustrum, and it will also give you the thickness for this frustrum as well as this frustrum, because the only difference between all these is this big D. That's all. D is constant, E is a matter of material, pi is a constant. So there's nothing different about all these frustra except this smaller, this D. Here the D is this one. For the next one, the D will be this one, smaller of the two, because there is an outer diameter here and outer diameter here, but we are focusing on the smaller diameter. So the big D is different. This one, actually this one is equal to this one, but this and this is different. If you only make sure that you get your D's right, then this expression gives you the answer to all problems. So this is the general equation applicable to all cases. Now this is 820, very famous equation in your textbook, 820. You are going to use it again and again. Now some discussion about this. This D is known. This D is the major diameter of the bolt. But what about D? Again, experimentally, D is 1.5 into D. So what we are talking about here is we want to find out the compressed area or the compressed diameter here, and what that is in this case, that is simply 1.5 times the diameter of the bolt. Experiments tell us. So it's good to use this one. But obviously, as far as this one is concerned, diameter 1.5 times the diameter will work. Similarly, on the opposite side, there you have a nut here. Again, 1.5 times the diameter will work. What about this? If you are using the same equation for plate 2, Now this diameter is not 1.5 times the diameter of the bolt. Obviously there's a difference between this diameter and this diameter. So for this case you will have to use some trigonometry. You know this d, and you have to add this part, but you know this angle is alpha, so you can use simple trigonometry and find the d here. So that is not difficult. That is in fact very easy. I'll just summarize this what I just said in the form of a diagram. This is the situation. First plate ended here, and then there are two more. There are actually three frustra. So d here is, in this expression, d here is simply 1.5d, and by d I mean this d. But when we use the same and the same d will be used if you consider this frustum. Again, these first and third have the same d. Obviously thicknesses will be different. This has thickness t1, this will have thickness t2, this will have thickness t3. Obviously these will be different. But what about d in this second frustum, this one? Obviously it's not 1.5 diameter of the bolt. Here you know d, plus you also know this angle is alpha, and this is t1 in this case. So for this d will simply be d plus 2 t1, 2 because you're talking about this plus this, you have to add the other side also, tan alpha, which is actually, if we're talking about 30-degree, then actually is d plus 2 t1 tan 30-degree, as we have been using. Let's call this d1, let's call this d2, and you don't need to consider this d because the formula takes care of that. Now if you are able to use this formula and calculate k1, then k2, then k3, then you have the system 1 over km, 1 over k1 plus 1 over k2 plus 1 over k3. This is the general purpose equation. In this case there will be three distinct areas, so you just add the reciprocals of the three. Now what if this is the most complex situation? There are simpler situations where your job is reduced a lot. For example, first of all, if you have the same materials, for this, let's take this. Let's take a case where the first plate is the hole here. The first plate is this one, the second plate is this one. But now, and the area under compression will be the same as before. Now here, the difference being the two are of the same material. Then actually you don't need to do it thrice. You can only do it twice. Why? Because this distribution of compression, this doesn't differentiate between plates as long as the material is the same. As far as this distribution is concerned, this is just one material. Earlier we had to divide this into three. One part, this part, and then another part, this one. Why? Because a different material is here, and then the third part, this one. This material is the same. Simply take, you can simply take this as, if this is whole length is L, then you can take both of them, take T, and you just calculate this once. Actually, you have to do it twice, but actually you can do it just once. I'll explain how. These are the thicknesses. So what you do is, for in the last formula for T, we'll just put L over 2. In formula A, we can use, for T we can use L over 2 now here. But please also consider that in this case, whatever is happening here, actually we have converted this from 3 different frustra to 2, but actually we can do it just once. Why? Because whatever the answer for this will be, it will be the same answer for this, same K for the first and then the second. So in this case, 1 over Km will be 1 over K plus 1 over K, because there is no concept of K1 and K2 now, and Km will be K over 2. So if we use both of these in this expression, then we can directly get this equation, that is, now it will be for the whole member, so you don't even have to do it twice. Too long, this two, notice this 2 here has come here, and L replaces T. Let me explain what W is. I'll just explain it. This will give you the stiffness of the member straight away. This you don't need to do for 1 and 2 and then combine them, because we have already done it here. Notice this 2 here. Now this, you can see that dW has replaced the big D here. That is because in the general case you will have, sometimes you'll have this diameter here, and let's call the, in that case it's called washer diameter, because the washer is placed here, dW. But the same formula is applicable for this second frustrum also, and there this D is not washer diameter, this is much bigger than the washer diameter. But when you have this special case where you have the same material, it doesn't matter what the thickness of these members is. Actually what matters is that you have this situation where you have two identical frustra. So one starts from here, this is formerly D, now you call washer diameter. The second one, dW. There's no concept of this, there's a D here also, but you don't separate this and this, so you don't need that. So here we dispense with the big D and just use dW. Now we also, like earlier, alpha 30 degree, this is general probability expression. If we use an alpha 30 degree, and we also know that dW, because now there's nothing but dW here. In the original expression there was D, so D had value here at value of 1.5 times D, but here it was something else, so we couldn't replace that expression in that expression, this. But now there's just one washer diameter here, another one here, so you can just replace it. There's no other diameter, so just put in the values here, so your equation will be further simplified. This is another expression 822 in your book. This is a special case. The previous one was a general purpose case. This is a special case So either you'll be using 822 or you'll be using 820. 820 general purpose, any sort of situation. But when you do this, you have to calculate it a number of times and then use this reciprocal formula. But in a special arrangement where you have just one material inside, in that case, you can use this. In this case, you don't need to use this formula because this has already been included here. So this will give you directly the stiffness of the whole member, Km, all members. Here in this case, this only gives you K. So you will K1, K2, K3, but in this case, it will give you for the combination. Now, this brings an end to this particular discussion. But in case if you are wondering that we are only considering nut and bolt arrangements in this discussion, you need not worry about that because although I made this and the whole discussion revolves around nut and bolt, but if it's a cap screw, the situation is exactly the same. The only difference will be something like this. You have this, and now in this case, maybe this is your plate 1, this is your plate 2, and your L is this one, and you know how to calculate L. But your bolt will be maybe slightly longer than this length, and here will be the threaded part, and your bolt is slightly longer than the grip length, because you won't find the exact bolt of that size, the size required for this L. But apart from that, the same situation, the compressive area will exactly be the same like you have here. Just like there was compression inside this grip length L, started from 1.5D, ended at 1.5D and met at the center. The same thing happens here. Starts at 1.5D, this small d, ends at 1.5D, and it meets at the center. And this L is the same, although there is no nut here, but the distribution spans around this length L. So all these expressions that you have calculated, they are for nut bolt arrangement as well as cap screws and studs or whatever you are using.